Dr. Incognito. In this video, we're going to explore L'Hopital's rule. L'Hopital's rule is used to find limits. So if you're trying to find the limit as x approaches c of f of x over g of x, and if you're getting 0 over 0 or infinity over infinity, if you're getting either one of these classical indeterminate forms, then the limit can be computed by taking the derivative of each function. So instead of calculating the limit of f over g, you can calculate the limit of f prime over g prime. This is L'Hopital's rule. It is a consequence of what's called the generalized mean value theorem. So you're trying to calculate the limit of f over g. If you have one of these forms, then you can calculate the limit of f prime over g prime instead, and it'll give you the same answer. So let's look at some examples. Let's say we're trying to calculate the limit as x goes to 0 of e to the x minus 1 divided by x squared. If we plug in x equals 0, we get e to the 0 minus 1 divided by 0 squared. And since e to the 0 is 1, the numerator is 1 minus 1, which is 0, and therefore we have the form 0 over 0. So L'Hopital's rule says that this limit can be computed by taking the derivative of the numerator and the derivative of the denominator separately. It's very nice because you don't have to use the quotient rule. You do the derivative of the numerator, you do the derivative of the denominator, and you recompute the limit. So what does this limit equal? Well, as x goes to 0, we clearly have a 0 in the denominator, that's trouble. And e to the 0 is 1, so we have a 0 in the numerator. So this actually didn't appear to be very helpful. So what's the value of this limit? Whatever the value of this limit is, that's the value of the previous limit by L'Hopital's rule. So to figure out this limit, let's try L'Hopital's rule again. So L'Hopital's rule, limit x goes to 0. And I'm encouraged by the fact that I can see that when I take the derivative of 2x, I will get 2. And therefore, I will not have an indeterminate form when I finish here, because I'm going to be dividing by 2. In the numerator, the derivative is e to the x. So as x approaches 0 now, e to the 0 is 1. So I have 1/2. The original limit is 1/2. Using L'Hopital's rule not once, but twice. Let's look at a couple more examples. Let's calculate the limit as x goes to infinity of, let's look at a rational function. X cubed plus 4x squared minus 3 divided by 7 plus 2x plus 2x cubed. So this is a rational function here, polynomial over polynomial, and we're looking for a horizontal asymptote. We're calculating the limit as x goes to infinity. If we get a numerical answer for this, then the line y equals that answer will be a horizontal asymptote for the function here. Now, you may already know that in this situation the answer is the ratio of the lead coefficients. So x cubed, 2x cubed, the answer will be 1 over 2, which is 1/2. But this is also a nice application of L'Hopital's rule. We'll do it several times, each time getting infinity over infinity. And then in the end, we will see that the answer does boil down to 1/2. So let's check that out. First of all, as x goes to infinity, a polynomial will always either go to infinity or minus infinity. And you can just look at the lead term to determine which. As x goes to infinity, x cubed and 2x cubed both go to infinity. So this will have the infinity over infinity form. And so we can use L'Hopital's rule, take the derivative of the numerator, 3x squared plus 8x, divided by 2 plus 6x squared. It's still infinity over infinity. We do L'Hopital's rule again. Limit x to infinity. 6x plus 8 divided by 12x. It's infinity over infinity again. We can use L'Hopital's rule one more time. We'll do the trick. We get 6 over 12, which is a half. And that was the ratio of the lead coefficients here. 1 over 2 was a half. So the L'Hopital's rule method agrees with the ratio of lead coefficients idea. Let's take a look at another example. The limit as x goes to infinity of x squared times e to the minus 3x. So as x goes to infinity, x squared goes to infinity for sure. And as x goes to infinity, what happens to e to the negative 3x? 3x itself goes to infinity, so negative 3x is going to negative infinity. So how do we interpret e to the negative infinity? How do we interpret that? Well, a negative exponent means that we should be taking the reciprocal. So we should be looking at interpreting the reciprocal of e to the infinity. And e to the infinity is infinity, so we should be thinking about the reciprocal of infinity. And the best choice there is 0. So we have here infinity times 0. Which is not the right form for L'Hopital's rule. This is an indeterminate form. This is considered an indeterminate form. But L'Hopital's rule is for the classical 0 over. This problem has neither of those forms. It's infinity times 0. In order to use L'Hopital's rule, we have to convert it into one of the classical indeterminate forms, either 0 over 0 or infinity over infinity. And as the discussion of negative exponents indicated here, maybe we should consider moving this e to the 3x into the denominator as follows. So we could rewrite this limit as the limit of x squared over e to the 3x. Now, when we look at x going to infinity, we have an infinity over infinity situation. And we can apply L'Hopital's rule. You take the derivative of the numerator, 2x. You take the derivative of the denominator, e to the 3x times 3 by the chain rule, so 3e to the 3x. Then limit x goes to infinity, we get infinity over infinity again. And one more application of L'Hopital's rule will do the trick, because that numerator is going to give us a limit of 2. Value of 2, the derivative is 2. The derivative of e of 2x is 2. The derivative of 3e to the 3x is going to be what? It's going to be 9e to the 3x, because the derivative of e to the 3x will give us another 3. So the two 3's will multiply together to make 9. And now as x goes to infinity, we have the numerator is 2. And the denominator is growing and growing and growing, which makes this fraction shrink and shrink and shrink. So our limit is 0, which is telling me that the exponential function here is growing much faster than the quadratic function as x grows. And let's look at one more example. Let's take a look at the limit as x goes to infinity of x times the sine of 1 over x. So what's happening here, x is going to infinity, so x times sine x is infinity times, let's analyze this one's a little more complicated. As x goes to infinity, the reciprocal 1 over x goes to 0, and the sine of 0 is 0. So I have infinity times 0, which is the same situation that happened in the last example. In the last example, we turned it into a fraction by simply taking advantage of the negative exponent right there. E to the negative 3x naturally becomes e to the 3x in the denominator. In this case, it's not so obvious. Neither one of them naturally falls to the denominator. But you can always rewrite an expression, a times b. You could always rewrite it if you wanted as a divided by 1 over b. You could always turn it into a fraction in that way. A little bit clumsy and artificial, but nonetheless turning a product into a fraction. Because L'Hopital's rule prefers fractions. And you could have moved the b down or the a down just the same. So I'm going to take that x and I'm going to write it on the bottom as 1 over x. So taking the sine of this angle and multiplying it by x is the same as taking the sine and then dividing by 1 over x. These two expressions are equal. And now, if I look at, analyze the limit, as x goes to infinity, 1 over x goes to 0. The sine of 0 is 0. So we have 0 over 0. So try L'Hopital's rule. The derivative of 1 over x is negative 1 over x squared. Using the power rule, 1 over x is x to the negative 1. So its derivative is negative 1 times x to the negative 2, which is what we see there. And the derivative of the sine of 1 over x, by the chain rule, it's the cosine of 1 over x times, that's the derivative of the outside, times the derivative of the inside, which is negative 1 over x squared. So again, the derivative of the sine of 1 over x requires the chain rule. It's the derivative of the outside times the derivative of the inside. The derivative of the outside is the cosine of 1 over x, and then times the derivative of the inside is minus 1 over x squared. And lo and behold here, the negative 1 over x squared simply cancel. The quantity over itself, that cancels out. And our limit, let me just rewrite it here. Our limit is now simply the limit of the cosine of 1 over x. And as x approaches infinity, 1 over x approaches 0, so we're getting the cosine of 0, which happens to be 1. So our limit is 1. Okay, that's a look at L'Hopital's rule. Thank you for watching.